in the last class, we learned about a few things about polymer. We learned about what we call what is polymer, how is polymerization is carried out, either using the addition polymerization or condensation polymerization. We also learned some classification of polymer, synthetic versus the natural, and also classification based on the molecular structure, the linear, the branch, the cross-link, and network. So today we want to see something that is unique to polymer. We want to discuss about three phenomena that is related to polymer. So three phenomena that is related to polymer, and this is important when you try to process or design any polymeric material. For example, plastic, you want to make a plastic, these three phenomena you need to take care of. What is these three phenomena? The first one is basically the crystallization. The second one is basically the melting phenomena. And the third one is glass transition phenomena. Glass transition phenomena lah. So today we will discuss only these three things. In the next class, next week, we discuss about the type of the polymer itself. For example, the name of polymer, thermoset, thermoplastic, and so on. But today, we go to this fundamental part lah. What crystallization, melting, and glass transition have to do with the polymer. Okay, first I go for crystallization first. Let's go for crystallization first. Okay, I go this. Let's put crystallization first. In previous class, we already see what is crystal. During the during the ceramic class, I show you about the sand is made up from the crystal, and the crystal is something that having. If you talk about crystal, normally people think something like this. Okay, a crystal. This is crystal. So a crystal, typically, it's like this. The characteristic of the crystal is that it has facet. So this face, we call it facet. Facet. The face lah, the face. Facet. The crystal here occur naturally, mean that there are nobody cut the crystal in such a way, because in order to make something like this, normally people need to cut using a tool and so on. When you go outside, when you see a stone or whatever, you see something like this, like just an irregular shape. But a crystal have a definite shape. The reason why the crystal have this definite shape is because on this surface, they are like a crystal, like the atom basically aligned in regular pattern. So that's why you get a very smooth space. So what we call the term crystal itself is basically a solid material that what we call that have regular arrangement of its atom. And this we learned before. This arrangement can be something like this. So can be something like this. So the crystal, for example, you have the atom aligned like this. 1, 2, and 3. So this one of the type of the arrangement, but also the regular arrangement can also mean the pattern itself is regular. For example, if you have something like this, and then you have something like this, you have, for example, regular arrangement of what we call of this honeycomb structure. So this also we call it like a crystal lah. They under the category of crystal because it have this regular arrangement. Imagine there are atom here, atom here, atom here, atom here, atom here. Even though this atom doesn't sort of like in one line, horizontal line or vertical line, it have a pattern. So this what we call the unit cell lah. So one pattern, we call it the unit cell lah, unit cell. So and this unit cell repeated again and again. So this also considered as a crystal lah. So that is basically the idea of crystal. Okay, so the crystallization is basically in polymer. The crystallization is basically the transformation. This is generic about crystal. Generic idea about crystal. The most important thing, it must be solid lah. You see, crystal must be solid. If you have liquid, of course, we have a liquid crystal, but for example, your calculator, the pin, you have the calculator here, and then the display there, there are liquid crystal there. But liquid crystal means that the liquid, for example, the liquid, normally they haywire, right? They sort of like move here and there. This is like the nature of the liquid. Liquid crystal meaning that the reason here in the calculator, they put liquid crystal. Liquid crystal. So liquid crystal, what does it mean by liquid crystal is that if this is a liquid and if you put the electric, suddenly this, whatever this thing, imagine this is just the substance lah. They suddenly become sort of like a line somehow. So that's what basically named liquid crystal. But if you look here, it still have this periodic arrangement. Okay. So the idea for the crystal is typically a solid material that have the regular arrangement of its atom lah. Typically it's solid, but sometimes you heard the word liquid crystal, just remember that liquid crystal has also what we call the arrangement like that. But we will not deal with that. Where is the duster? We don't. This is just a side notes only lah. Okay. So crystallization in polymer is basically the transformation of molten polymer, molten liquid, or molten polymer into the what we call liquid melt. Normally we call it liquid melt. Liquid melt, and this liquid melt have what we call highly disordered arrangement into what we call ordered solid lah, solid. So that is basically crystallization lah. So it's basically this thing is basically a phase transformation. Phase transformation. Phase meaning that the phase is just a phase lah. Meaning that phase, you know, you have a gas, you have a liquid, and you have a solid. So this transformation is basically from the liquid to solid lah, to solid. So that's basically what does it mean by phase transformation. So crystallization is basically under the category of phase transformation. You transform something into another thing. Okay, but this phase transformation for polymer doesn't occur. Okay, let me put this here. Okay, this phase transformation for polymer, it doesn't occur instantaneously. So it doesn't occur instantaneously lah. What does it mean is that if let's say you want to turn this liquid into the solid, what will happen first? They will need a nucleation, and then followed by the growth, and then followed by the what we call the equilibrium lah, the termination or equilibrium lah, equilibrium. What does it mean by nucleation? Is basically the formation of numerous crystal. So imagine you have this, for example, a polymer, a liquid melt polymer. So this, let's say, imagine this is a liquid melt of any polymer. So in order to transform this into solid, this thing will need to crystallize. But the crystallization doesn't happen in just like a blink of eyes. What happened first, they need to undergo this nucleation. Nucleation basically, suddenly they are what we call a small crystal. Let me put in the green lah, because this is green. So the small crystal will what we call form, and then this crystal will grow, and then until equilibrium, you what we call the transformation will be complete, and you get this thing lah. You get the solid lah. So in polymer, this crystal, okay, in polymer, let's say I take this crystal. In polymer, we know the polymer is what? Polymer is basically a chain of a molecule, right? So you have a chain of molecule. So this is the definition of polymer, a chain of molecule lah, that repeated again and again. So how this become crystalline? So this turn to crystalline by folding. This is not crystalline. This is just a chain of polymer. So normally when we say crystalline polymer, this chain we will fold like this. It just fold like this. So that's what we mean by crystalline polymer. The chain, they have this what we call the fold. They fold in such a way that you have this regular arrangement again and again. So this we call it lamellae. Biru lah. This thing we call it lamellae. Okay, lamellae. So that is basically the when we talk about the polymer crystallization, this is what does it mean by the crystalline part of the polymer. But in polymer, there are no 100% crystalline polymer. Okay, there are no 100% this. For example, let's say you have this solid. It's not like everything like that. It's not everything like that. It's not like everything like that. Okay, because there are no 100% crystalline polymer. Crystalline means perfect lah. Everything is perfect. I mean everything in order. But in a polymer, this thing, there are something like this. Okay, this thing also can sort of like make a stack again. For example, you have something like this, and then you have another one at the back, and then you have another one here, and then you have another one at the back, and then you sort of like get something like that lah, something like that. Okay, so this stack is stack. So the lamellae can stack on each other lah. However, in polymer, they doesn't have this happen throughout the bulk material. What normally occur is that you have something like this. You have something just, for example, here you can see here the what we call the end, or what we call the one that is not crystallized. They just protrude outside like that. So this part, the black part here, we call it crystalline part lah. Crystalline. The one that is not full, we call it amorphous. 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 Polymer. So if you look, the polymer in any solid, in any polymeric solid, you have a mixture of crystalline and amorphous material. Okay, and this thing, sometimes this lamella, they behave like this. Sometimes you get something like this, because here nucleation, they start with something small. So imagine you have the lamella here, and then sometimes you can have lamella something like this, and then it's grow lah. This grow. For example, imagine I grow this way. So you have lamella here, and then some what we call some amorphous region, maybe here, maybe here, maybe here, maybe here, maybe here. So this is the, let me draw in other color lah. So let's say this you have amorphous region here, 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 here. So if you look here, the center of this is here. So when we say it's grow, it's typically like this lah. Typically like it's grow lah, it's grow. It become bigger and bigger and bigger. Normally it's grow like this, or it can stack like this lah. So this basically, if this is called lamella, lamella is just one something like this. This is called sporulate. spherulite. S-P-R-E, spherulite. If you look the term sphere. So here you see in 2 dimension, but in reality the growth is basically in 3D. So you are basically get like a sphere of this crystal. Okay, so this sphere of crystal, they are dispersed in the solid polymer lah. So let me show you example of that. So easy if you can see. Spherulite. Let me put first. Okay, image. Okay, so if we have a picture, it's much easier lah for you to understand. Okay, so basically, if you look under the good microscope, you can see something like this lah. Something like that. Spherulite. This spherulite. So you can see spherulite is made from the what we call the fold, the crystalline part. Okay, so it's 3D, 3 dimension. Here you see from the front, but imagine it's like expanding all directions, so you get like what we call the sphere lah. So let me put spherulite polymer, polymer microscope. Let me put there. Ada 44. What is 44? Okay. So you can see something like this. Okay. So it's grow. This is like a nucleation, start from the knee and then it's grow. Okay. So this under the microscope you get something like that and something like that. So that is the polymer lah. Okay. So this if you see using the phase contrast microscope, you can see something like this lah. For the polymer, it's like that. You can see here the polymer. You have like something like this, but it also have this amorphous region lah. Amorphous region and so on. Okay, so like that, and so on. So that is spherulite and lamellae lah. Okay. Okay. So the reason why I show you about this spherulite lamellae is because, as I said before, there are no 100% crystalline polymer lah, polymer. So if let's say I draw what we call a graph, not a graph, a line here, and then this is 100%, this is 0%, this is 100%. And in terms of crystallinity, let's say I put here crystallinity, then the polymer typically somewhere in between here, okay, somewhere in between here. So we call polymer, normally when you heard people say crystalline polymer, what does it mean is that they are not 100% crystalline, there are some amorphous. So the proper ways to talk about polymer is normally people talk semi-crystalline polymer lah, because it has both the crystalline and also the amorphous polymer. So whenever people talk about crystalline polymer, what actually they mean is that it is semi-crystalline polymer. Okay. So example of highly crystalline polymer. Highly crystalline polymer is is polypropylene, Kevlar, nylon. So this is example of highly crystalline polymer. Polypropylene, this is polypropylene, mean that you have poly and then you have propylene repeat units lah. And then you have Kevlar. Kevlar is the what we call the fabric that people use for what we call for bulletproof jacket. The Kevlar and nylon. That's example of highly crystalline polymer, meaning that there are more percentage of crystal, I mean this lamella and so on, than the amorphous. Okay. Example of highly amorphous polymer, highly amorphous polymer is example like the rubber, like a rubber, polyisoprene. So this is rubber, and then you have also polycarbonate. Basically, polycarbonate is used for what we call to make a helmet visor. Helmet, you have the plastic, right, the transparent thing. So that is polycarbonate, and also CD, also made from the polycarbonate. Other is apa lagi? Polystyrene. This is just example lah. There are many more, but this is just example. We will learn about alloy. We will learn about this polystyrene, what is polystyrene, and so on in the next class lah. But just for now, I just give you the idea. They are polymer, they are highly crystalline, they are polymer, they are highly amorphous. Okay. So now it's about crystalline and amorphous. So I want to introduce a little bit the concept. While we are here, I want to introduce a little bit the concept about the concept of annealing. Concept of annealing. Okay. Because you need to get some idea about crystal, what is polymer, what is inside polymer first before we discuss other things. So now I want to introduce the concept of annealing. Annealing is basically the heat treatment. Heat treatment. Typically, you heard the word annealing in metal. Let's say I have a metal like this. So this is already cold. Okay. So this is what we call cold work metal. Let's say you have this metal rod. This is cold work metal. Mean that it's already there lah. It's already finished lah. So annealing, what does it mean by annealing? This cold work metal is basically you try to heat this thing. Okay. Normally you heat the metal to melt it and make another metal. But annealing, what does it mean by annealing? You try to heat it. When you heat it, you don't melt it yet. You heat it not to melt it. You take a metal and then you try to take a torch and then you just heat lah. You have a torch here, you just heat this thing. Metal, not to melt it, but what happened actually when you heat this metal, something happening at the microstructure inside the metal. When you hit the metal, something happening to the structure of metal. And normally people anneal, what we call anneal metal in order. Why people anneal this metal? In order to make it more ductile. Okay, make it more ductile. What we call, and soften the metal lah. Soften the metal. And this happen because there are change in microstructure in the metal lah. For example, let's say you want to sort of like make a ring out of the metal. Like for example, the thick metal like this. When it's cold, it's hard to do something, anything to this lah. But when you anneal, you are basically heat this thing, and then you make. It's not like the idea. Of course, you understand when you heat, and then it's easy to bend, right? But the idea of annealing, you heat it, and then you left it until it's cold, and then this is cold, and then you can bend it. Normally, you understand when you heat the thing and it become what we call red hot, you can always bend it easily. But the concept of annealing is happen after you cool back the heated rod. You heat this thing, something happen inside the rod, and then you cool it back, you let it cool, and then that metal now, the one that's already annealed, is totally different than before. The structure inside is totally different than before. And now you can, if I do like this, you can sort of like bend, and you can make a ring and so on lah. Okay. So it's not about you bend during the heating. You bend after it's cool. Lah. So that's the concept of annealing. the structure change inside after it's become cold again. Okay. So the annealing is basically a concept in metallurgy lah. Metallurgy. So it's basically heat treatment lah. Heat treatment. So it's common in metal, but it's not so common in what we call in polymer. But there are cases that people try to anneal a polymer. For example, let's say you have in polymer, let's say I draw here. Let's say you have a polymer. Polymer. Now we talk about polymer. Even though it's not as the concept of annealing is not so much relate to polymer, more relate to the metal, but in some case, people also anneal the polymer. So let's say you have some thick block, thick cylinder of a polymer, for example, PVC pipe. Let's say you have PVC pipe. Let's say this PVC pipe. Let's say you have PVC, and this PVC pipe is very thick. Let's say this PVC pipe. It's very thick. Okay. PVC, because what we call because polymer have its amorphous and crystalline, okay, they are mixture of amorphous and crystalline. They have a lot of internal stress inside the what we call inside the material. They have high internal stress. It's like when you have a glass. Last time Farah come in front, and I give Farah like what we call the glass slide, right? And then if I try to break like that, it just shattered. So basically, what does it mean? That there are a lot of internal stress inside the glass. So when I apply the outside stress, it just shattered here and there. If you have something crystalline, they are not I mean, if you have something crystalline, it's strong. So you unable to shatter lah. So normally the amorphous material, they have a lot of internal stress inside lah. For crystalline material, we don't talk about the internal stress inside because crystalline material is typically strong lah. So we don't talk about breaking it and so on lah. But something amorphous like glass, totally amorphous, there are a lot of internal stress inside the thing. Okay, if you try to apply load outside, the stress inside will be sort of like burst lah. So imagine you have this PVC, the thick, what we call thick PVC pipe, and PVC being a polymer is have both amorphous and crystalline. So the amorphous part and crystalline part, they act together and they create a lot of internal stress here. That's why if you try to sort of like gergaji apa? Saw, let's say you try to saw this PVC pipe, sometimes it's cheap. Okay, you have a plastic, let's say plastic, and then you try to saw it. Thick plastic, perspex or whatever, you try to saw it. Sometimes you will see when you saw this thing, it chip, meaning that it just chip like that. It just chip like this. Instead of getting what we call like this lah, the chip like this. They just chip crack. Try to take CD, the compact disc, and then take a scissor, try to cut it. You will see it's not cut like you cut a paper. It will sort of like chips here and there. So that's meaning that there are a lot of internal stress inside the CD when you see the chip there. So annealing of polymer is done in order to soften, to reduce the internal stress inside this thing. So what they do is that they heat this thing. They not heat. Okay, in polymer, they are not heating it. They are more or less, because polymer, one of the drawback of polymer is that it's heat sensitive. If you hit a polymer, then you are basically damage the structure and so on lah. So the way how they anneal this thing is basically by adjusting, controlling the heat of cooling. Because annealing is heat treatment. It can be heating or cooling. It's not necessarily just heat alone. You can heat or cooling. So in case of polymer, normally we deal with the cooling part lah. So when you want to make PVC pipe, it start with something molten, liquid melt. Liquid melt. any polymer, in order to make this PVC part, it start with some virgin polymer. It start with the, let's say I show this. Everything, when you make a plastic, it start with this. Virgin polymer pellet. Okay, when you want to make any plastic, this or that and so on, they start with this. This is a pellet. Okay, for example, to make this chair, what the manufacturer does is that they buy this thing. They buy this what we call the pellet. So for example, this like from what? Let's say from PP, polypropylene. So they buy this. They buy this polypropylene, what we call? Pellets. And then they put in the machine, and the machine mold in such a way, get this thing. So it starts with this thing. So in order to get this structure, you need to melt this first. So during melting, it melt lah, this melt. And then in order to shape this thing, they put the melt. So you have, let's say you have this chair. Let's say I draw the chair like this. So let's say this is like, let's say this is, okay, let's say this is a chair. So this is chair lah, chair, meaning that there's a hole lah, hole. So this is basically the mold. So let's say this is the mold. So basically what they did is that they pour the melt polymer inside the mold, and the mold the polymer will assume the shape of the mold, and then during cooling, okay, it will harden. So the annealing of this polymer normally happen whether you cool it fast or cool it slow. Okay, if you cool it very slow, okay, this thing. If you try to cool very fast, okay, it will yield a lot of high internal stress inside the what we call inside the end product. What I mean is like this. I give some idea lah. Let's say the water, the water you want to turn to ice. Water you want to turn to ice. Okay, water you want to turn to ice. So how you turn water to ice? You put into freezer, right? If you put a glass of water in the freezer, you don't see that the water turn to ice straight away. It takes time, right? So when you put water in freezer, you are basically doing a slow cooling. You cool the water at slow rate. Okay. There are another way to make this is basically you put water instead of inside the freezer. You put in liquid nitrogen. Liquid nitrogen is basically liquid nitrogen that is in liquid. So the temperature for this is 196 Celsius, negative 196 Celsius. So let's say you have a glass of water, and then you put in a box that contain a liquid nitrogen. Liquid nitrogen, what will happen, because the liquid nitrogen have very low temperature, the water will freeze instantaneously instead of waiting time. So this is, it takes time lah, slow cooling rate. This is what we call fast cooling rate. Okay, let me show lah. Easy, liquid nitrogen. Liquid nitrogen, what is the thing? Liquid nitrogen. Okay, so basically you have something like this. People make ice cream. If you go to a high-end cafe or whatever, people make ice cream using this liquid nitrogen. Okay, so basically it's just a liquid and it's very cold. It's very cold. Okay, so see ice cream. So you can play. It's fun to play. So basically, if you have a glass of water, you put inside this liquid nitrogen, the water will freeze instantaneously. So when that happens, when you cool instantaneously, what happens in a water? You see, in a water there are what we call oxygen and also hydrogen, right? H2O. So when things cool, is basically this molecule, water molecule, will try to rearrange themselves to make a crystal. to make a crystal. So for example, in the liquid, this you have oxygen, you have another one here, another one here. So when you try to cool, let's say this in liquid, let's say in this liquid, this molecule and this molecule is moving here and there. So when you try to cool, this try to reorient themselves so that this O will sort of like make a hydrogen bond there and so on. So they try to sort of like enter a configuration lah, try to self-assemble themselves so that you get ice lah. So when you try to cool very fast, you put into the what we call into the liquid nitrogen, this thing doesn't have time to reorient themselves. They just cannot reorient in perfect manner lah, because water, if you make ice, this thing they make the hexagonal pattern lah. That's why you see the snow is hexagonal, because the reason why snow is hexagonal is because have something to do with the molecular structure of the water, make a hydrogen bond and so on lah. So you get hexagonal. But if you try to cool this water very fast, you don't have the structure. It's like you have a glass. I mean, you have, it's still ice, but the structure inside the ice is different. Okay, you still get ice. Both of these you still get ice, but the structure inside the ice is totally different. Here, when you cool very fast, there are no structure. There are no structure lah. But if you freeze slowly, like in the what you call inside the freezer, you get some structure. So if I put here ice in freezer, mana dia? Ice crystal, freezer crystal. So you get something like, yeah, you see something like this lah, because it has time, that snow, it has time to grow lah, So you see something like this. The reason why you get something like shape and so on is because it has time to grow and reorient themselves and get the ni lah. So for coming back for this thing, if let's say you cool it so fast, you cool this thing so fast, PVC so fast, then they are what we call, they are no, the molecule inside this doesn't have time to rearrange themselves into what we call into this spherulite and so on. So when it is mostly amorphous, it's easy to what we call to break. Okay. So in order to reduce this high internal stress, annealing is done. How they do it is basically by slowing the cooling rate. So that's how they do it lah. They slow the cooling rate lah. They control the cooling rate. So that's basically the annealing lah. It has something to do with the crystallinity lah. So if you have amorphous material, you lower the cooling rate in order to reduce the high internal stress. Okay. If you have amorphous material, let's say you have amorphous material, you basically lower the cooling rate in order to reduce the high internal stress. Okay. Okay. But if you have semi-crystalline material, okay, meaning that inside the material, inside the liquid melt, there are also the crystalline and so on. So when you try to sort of like lower the cooling rate, what you get is that they have more time for this semi-crystalline material like polymer to get to what we call, to make this crystalline structure. If you use a lower cooling rate for semi-crystalline material, for example like a polymer, you are maximizing the crystallinity of the polymer itself. Okay, if you have totally amorphous material, when you lower the cooling rate, you basically reduce the high internal stress. Okay, when you have totally amorphous material, if you lower the cooling rate, you basically, what you do is basically you minimize the internal stress lah. Okay. So that's what you did lah. So normally annealing in polymer is depend whether the polymer is highly amorphous or highly semicrystalline. Okay. When you try to, the idea is this: when you try to cool something slowly, the molecule have time to reorient themselves. Okay. Reorienting themselves meaning that it try to get into a pattern. So what does it mean by this lah? So that's why for semicrystalline material, if you cooling at a low cooling rate, you are increasing the crystallinity. For amorphous material, totally amorphous material, when there are no crystallinity inside, if you lower the cooling rate, okay, because it's just amorphous, so there are no crystal form, the lowering the cooling rate is just help to minimize the internal stress lah. So that's the annealing in polymer lah. So we learn about the crystal. The polymer have what we call the amorphous part and also crystal part. We learn how the crystal is grows. Typically start with nucleation, grows, and then is terminate by equilibrium. And then we learn also about no polymer that is 100% crystalline. Is typically in the middle here, in between two extremes. And normally we call polymer semi-crystalline lah, because inside the polymer there will be some crystal, there are some amorphous lah. Example of the highly crystalline polymer, highly amorphous polymer, and then we also introduce the concept of annealing. Annealing is typically associated with the metal, where you heat the metal to change the structure inside the metal, so that after it's cooled back, there are some change in the properties lah. But for polymer, normally we deal with cooling down lah, because annealing is heat treatment. It can be cool or heat or cool. So when you try to anneal polymer, it depends on the polymer itself. It is highly amorphous. You anneal the polymer by lowering the cooling rate during the production. By doing that, you are basically minimizing the internal stress, so that when you cut it, they are not cheap. But if your material, if your plastic is semi-crystalline in nature, when you try to lower the rate of cooling during the production process, what you did is basically you increase the amount of lamella. I mean, you increase the crystallinity. So you maximizing the crystallinity by annealing the semi-crystalline material. The more crystalline a material, the stronger it is. Okay, the more crystalline the material, the more stronger it is. So we're done with the crystallization. Let's talk a little bit about the melting. The melting part. Okay, let me close this. Okay, melting is basically the reverse of crystallization lah. Okay, just simply a reverse of crystallization. So let's talk about melting. Mana? Melting. Melting. Okay, number 2. Melting. Okay, it's basically transformation of highly ordered structure to viscous liquid lah. To viscous liquid that consists highly random structure. Okay, so basically melting is just from the very crystalline, very what we call highly ordered structure, you turn into the highly random structure lah. And random structure typically is liquid lah. It's liquid. Okay, this melting happen happen at melting temperature lah. Melting temperature. We call it Tm. We call it Tm. Okay, melting happen at melting temperature. The melting in polymer is quite different than melting in metal or ceramic. Okay, melting in polymer happen. Okay, what make this melting in polymer different than metal and ceramic is that first, it take place over range of temperature. We will discuss this later. Temperature, and also second is basically the behavior, melting behavior. What we call they are depends on the processing history. For example, whether the material is annealed before or not. So it depend on the processing history lah. In particular, their crystallization temperature. Okay, melting behavior depend on its polymer processing history. For example, if you try to anneal the polymer before, and then later on you want to melt, that's make a difference. If you try to compare with when you try to melt a polymer that is not annealed before. So it depends highly on the processing history, because when you to make a polymer, you need to process it first. To make a chair, you need to process first. How to make a chair? If you try to slow cool this thing, or you try to fast cooling this liquid polymer in order to make this chair, it will affect this melting behavior later on. So it's important, because if you see before, we have this lamella thing, okay, lamella fold or whatever. The amount, the thickness. For example, you have this thing like the thickness play a role. The thickness of lamella. The higher the thickness, meaning that the higher the thickness, the higher the crystallinity lah. Crystallinity, meaning that the higher the melting point lah. So that's the thing. And how to increase the thickness of lamella is by annealing lah. If you try to anneal using the slower cooling rate, then you get a lot of lamella lah. And by doing that, you will increase the thickness, you increase the crystallinity, and at the same time you increase the melting point. So it's connected with each other lah. And also the impurities. If let's say you have impurities, let's say you have impurities. Let's say you have a lot of impurities inside the polymer itself. You are basically lower the crystallinity lah, because the impurities will sort of like be in the between this lamella. So you basically lower the crystallinity, and basically you lower the melting point. So that's basically how this crystallinity relate with the melting. Okay. When you have metal is normally 100% crystal. The molecule inside the metal is perfectly arranged. So it doesn't depend on the how much crystalline the metal, because metal is normally 100% crystal lah. But for the for the polymer, it's highly depend on how much you have this lamella inside the bulk. Okay, so that is basically the melting lah, the melting part. Okay, this normal lah. Melting is just from the solid to the liquid. Okay, the third part is glass transition. Okay, here I don't discuss yet this the first part. I discuss the second part only. The first part has something to do with the glass transition. So let's turn to the glass transition part now. Okay. So the glass transition. So the glass transition phenomena. phenomena. The temperature at which this glass transition happen, we call it glass transition temperature, and denoted by TG. Okay, it's basically the temperature where a polymer turn into glass light. Okay, what is glass transition phenomena? It's a phenomena where what we call, where there are reduction in mobility, in motion of amorphous region in polymer Okay, so you see the first thing, there are reduction in motion, and second, amorphous region. So imagine amorphous region, you have something like this. This is crystalline, and then you have the amorphous region. Okay, this amorphous region being like this, it can wiggle around. Wiggle around. Okay, it's like a spaghetti. It's like a spaghetti. So what happens when you put spaghetti inside the freezer? It will sort of like crust lah, become hard. When you put in freezer, it become hard, it become brittle. Okay, it become hard, it become brittle. So that's actually happen. That's what does it mean by glass lah, like a glass. So because polymer have this both this crystalline region, and also the amorphous region. Okay, because of this, it will the glass transition phenomena will happen only on this amorphous part lah. Okay. So crystalline region will sort of like will experience the TM, the melting, melting temperature, this thing. Okay. The amorphous region will experience the TG. Okay. So that's why when you see a polymer typically got TG and also TM. The glass transition and also TM. The glass transition phenomena happen when this amorphous region start to become like a glass lah, melting is basically when you see the melting, transformation of highly ordered structure. This meaning that the crystalline, the crystalline part to the viscous liquid. So basically this unwind the thing. So the glass transition temperature, so let me talk about this. Above TG, the polymer become glassy. We call it glassy state. Below TG pula. Terbalik ni. Okay, above TG, below first lah. Below TG, it behave like a glassy state. Above TG, rubbery state. Okay, what does it mean here? If you have, for example, let's say I give example rubber. Rubber have TG around -70 Celsius. So this for rubber. So meaning that above TG, you get something that can move, right? Rubber tire. This is like tire kereta. Okay. Above TG, normal ambient temperature, the normal temperature like this, 25 Celsius. If you have a tire here or rubber, whatever, you can see it's like rubbery. Okay. But if you cool the rubber down to less than -70, the rubber become like a glass, like hardened like glass. So that's what does it mean by TG lah. Another example is your bottle, plastic bottle. Another example, plastic bottle. Plastic bottle. Plastic bottle, PET, polyethylene terephthalate. So plastic bottle, the one that normal bottle, PET, the normal PET here. PET bottle. So you see the PET bottle is like that. So that is PET from PET. So this PET have a TG about 70 Celsius. 70 Celsius. So the plastic bottle now you use if you have a plastic bottle now, you can see this plastic bottle at the normal room temperature. So normal temperature is around 20 to 30 Celsius, right? So you can see the plastic become hard, like hard lah, like hard. But if you try to heat this thing beyond 70, you get the TG. This thing becomes softened. It's not melt, it's softened. Let's say you put this in 80 Celsius. It's not melt yet, okay? Because melting point for the PET is 200 something, okay? TM for the PET is around 200 something lah, 200 something like that. 200 something like that. 180 to 200 something like that. So when you try to put this in a place where the temperature is around 80 Celsius, it still look like this, but something happened at the molecular level. It's sort of like what we call, it's softened. We don't call it melt yet. We call it, it's above the TG. So it behaves like a rubber. And then if you increase the temperature further, you will see that it start to melt. That is TM. Okay. So the TM occur when the crystalline part of the bottle start to unwind. This TG part, when you put this bottle at 80 Celsius, what will happen? This thing will start to, now at the normal temperature, the amorphous part is just freeze in motion. But if you put in the place 80 Celsius, this start to wiggle around. That's why you get the thing softened. This is different when you have metal. Metal, you heat it, it's softened, but it's not like this. It's more like it will melt later on.